So we did example 1 yesterday. We derived the formula for the volume of a sphere. And the way we generated the three-dimensional volume was we took a region, an area, and we rotated it around the x-axis, 360 degrees, and that generated a three-dimensional object. So we call those objects in general volumes of solids of revolution, okay? Revolution, because we're revolving them around or about an axis. All right, so when we did that yesterday, our cross-sections, which were perpendicular to the axis of rotation, ended up being little tomato slices of varying radii. And so those are also known as little discs or little cylinders. So the formula in general that we're using is the area function as a function of x times dx, which is your third dimension, giving you volume. So if we can write the cross-sectional area as a function of a variable, then we can integrate it from left to right. And our cross-sections were circles, which is pi r squared. And so anytime your cross-sections perpendicular to the x-axis give you a solid, it's going to be a disk. And so that's where we summarized this yesterday. So the disk method is going to be pi r squared h, which is the volume of a cylinder. But instead of h, we have dx because it's infinitely thin. We pull the pi out front. We just have to remember to square the radius. Okay? So that's all that is. That's the formula for the volume of a cylinder with dx instead of h and the pi factored out. All right, so when are we going to use this? Again, the mnemonic was, instead of perpendicular, you say perpendicular. And that tells you how you're going to be slicing it in relation to the axis of rotation. So here's an example that's more typical. Find the volume of the solid. So there's a volume. And by the way, volume, just like area, has to be what? What type of number? Positive, yeah. Find the volume of the solid form by rotating a region bounded by the x-axis, square root of x, and x equals 1, about or around the x-axis. So it's going to jump out at you. It's going to tell you the axis of rotation. But the first thing is, just like with area, you want to identify the region. If you rotate the wrong region, you're going to get the wrong volume. Okay, so let's do that. There's the y-axis, the x-axis, and the x-axis is also one of the boundaries. So I'll just draw that in there with a different color. The square root of x is right here. And then x equals 1, I'm going to draw it sufficiently further out over there. You don't want to make it too close to the y-axis, then your region looks very tiny, and you want to kind of visualize what's going on. So there's the region. Now, before you decide how you're going to rotate it, or before you even do that, if you were to find the area of that region, how would you prefer to slice it? Vertically or horizontally? They would both work beautifully, wouldn't they? A vertical would always be from left to right, radical minus the x-axis, and a horizontal would always be x equals 1 minus x equals y squared. So the equations will allow you, so either way is fine. But so that you don't have to solve your equation for x because it was already given solved for y, a vertical slice might be your preference simply because it requires a little less work. That would be dx. So what's going to happen, as it turns out, is you're going to always choose your preference for your slicing method, and there's going to always then be a method to accommodate how your slicing preference relates to the axis of rotation. But in this case, we're rotating it around the x-axis, which is a horizontal line. We only have one method, the perpendicular method, so we have to slice it perpendicular to a horizontal, which would be vertical. So right now, we have to slice it vertically. We don't have another method. Okay, so if you want to then envision what the three-dimensional shape will look like, that could be kind of fun. Reflect it across the x-axis and kind of give it like a 3D look right here. It's going to look kind of like a what? A dome. Yeah, kind of a half dome, turned sideways. Maybe like a headlamp, a rounded headlamp, or I don't know, I always think of a ham for some reason. Half of football. There you go. That's better. We'll go with that. Now, this right here is our radius of rotation, which I call big R. It's the radius of rotation. If you slice it all the way through vertically, through the entire solid, again, your cross-section is going to look like this. And here is the radius of rotation. And, of course, depending on where you slice it, at 0 or out at 1, You're going to have a bigger disk or a smaller disk. Yeah. Okay. So let's see if we can set it up. Volume, I'm not going to write out the whole word volume, but I'm not going to put V either. I'll abbreviate VOL. Because our cross sections are perpendicular to the axis, it's going to be the disk method. So the disk method is pi r squared dx from A to B. So I'm just writing it out in general. And if you put the square in between the r and the of x, that's fine. So now let's go ahead and plug in. We're going to be integrating from left to right. So we're slicing it from x equals 0 to x equals 1. And it's r squared dx. So the r in this is the same as the h in the previous section. The only difference is when you're finding the equation for the radius, one of them has to be the axis, either the top or the bottom, because otherwise you don't have a radius. So as it turns out, the curve, square root of x, is on top, and our axis of rotation, y equals 0, is on the bottom. So in this case, top minus bottom is curve minus axis. So it's the square root of x minus 0. That's top minus bottom. And there's your setup. Guess how many points that's going to be worth? 2. You're going to get 1 for your integrand, and then you're going to typically get another check for having your interval of integration with the correct constant pi out front. So now if we had to evaluate that, we would simplify our integrand, of course. Square root of x quantity squared is just x. And we evaluate it. Pi goes for the ride. We get a 1/2 x squared. And we evaluate it from 0 to 1. So now I pull the pi halves out front, plug in the top, and you get 1 squared minus plug in the bottom, 0 squared. Your answer is pi halves. And if you end up with a negative number there, something bad happened. More than likely, you don't have a reversal necessarily in here because you are squaring it. It should end up being positive, but you probably went from 1 to 0 or you plugged in backwards somehow. So that would be the volume of that half of a football. Ham football dome thing, okay? So not so bad if you remember the formula, right? Pi r squared dx. Not too shabby. All right, so the word of the day, one of them is perpendicular. Yeah, perpendicular. Slice it perpendicular to the axis of rotation. Your cross-section will be a disk. Pi r squared dx. All right, example 3, another one. Find the volume of the solid formed by rotating the region bounded by y equals 1, square root of x, and x equals 0 around the line y equals 1. Ooh, okay, a little more interesting. Step 1, identify the region. So we still have our old friend square root of x, but now we have a new friend y equals 1, which is this guy here, and x equals 0, which is the y-axis. So do you see the region bounded by all three of those? I'm going to move it up just a little bit, y equals 1, just so I can make the region a little bigger. It's this region here. Now the axis of rotation is still a horizontal line. We're rotating around y equals 1, but it's not the x-axis anymore. But still, nonetheless, because it's a horizontal line, we only have one method. It requires us to slice it how in relation to that horizontal line? Vertically, because vertical and horizontal are perpendicular. So here's what one of the slices would look like. And that's going to end up being your radius. Now again, if you want to envision what the three-dimensional shape looks like, you can kind of reflect it across the axis and then do your little three-dimensional thing right there. It kind of looks like a Hershey's Kiss, maybe. It's got this concave part. So you don't really even have to visualize that. All right, so one thing is, if we're slicing it vertically, we need to know our intervals of integration. You always integrate over the areas region, which is from 0 to this point of intersection, which is what? 1. Yeah, you could guess, right? The square root of 1 is 1. Y equals 1 is 1. Yeah, or you can set them equal to each other and square both sides. You get 1. So x equals 0 to 1. And we're ready for our setup. The volume is going to be pi integral from 0 to 1 of r squared dx. So if you notice how I do that, you don't have to write a separate equation for r. Just go to your integrand and put parentheses squared, and then you can come back as a second step and write the equation for r. It's your radius of rotation. The top curve in this case is the axis, which is 1, and the bottom curve is the square root of x, right? So guess what your radius is? 1 minus the square root of x. It's still top minus bottom, and one of them is your axis. And that, again, is your setup. That's going to be worth 2 checks, one for the integrand and one for the pi. So now if you had to simplify that, we're not going to simplify all of these because I'm going to assume that you know how to do that. But this one right here, what would we have to do in order to integrate 1 minus square root of x quantity squared? The inside function's derivative is not on the outside. We're going to have to expand it, yeah. So square, multiply double, and square. And now you have 3 terms. So pi for the ride, we get x. That's going to be an x to the 1/2 plus 1 is 3/2, and a 2/3 puts that as a 4/3, plus 1/2 x squared, evaluated from 0 to 1. So when you plug in the top, you get 1 minus 4/3 plus a half. And when you plug in the bottom, you get 0, which is nice. So whatever that comes out to be, let's see, that's going to be a negative 1/3. So 1/2 minus a third. Should be a positive number, right? That's really why I'm checking. That's going to be a pi 6. So that's one of our favorite unit circle angles, but in this case, it represents a 3-dimensional quantity. In cubic units, that would be the volume of that Hershey's Kiss looking thingy, majigger, mabobber. All right, so questions so far? We'll stop right there before lunch. In each case, we sliced it perpendicular to the axis of rotation, and our cross-section was a disc. All right, have a fantastic lunch, and we'll see you when you get back.